Welcome to the Grothingi School. This is the first lecture on the advancement of topological K theory. The speaker today is Professor Somnath Basu from ISA Calcutta. Today he's going to talk about sphere bundles, um, bundles over two spheres and Bott periodicity. So, yeah.
Okay. Yeah, thank you, Dipankar and the other organizers. So I couldn't attend a lot of these talks, although I wanted to, but I tried to look through on the YouTube channel, and I'm sure it has been a very, purposeful series of talks for many people. So, so in the two talks that I'm going to give this Saturday and the next, my plan is to essentially talk about Bott periodicity, its context, sketch of a proof, and some generalizations if time permits. Okay. So the plan today is going to be slightly different from what I announced in the abstract, but since there are different people attending these talks having different background, some topological, some algebraic, and so on. So let me start briefly by initially sort of, so like part A of the talk. Sorry. Okay. And so here we are going to recall certain basic constructions regarding vector bundles, clutching functions, and specifically talk about bundles over the two sphere. And we'll also recall some basic properties of the reduced K theory and define, recall the definition of the higher K groups. And in the part B, we're going to initiate a proof of Bott periodicity. So some of you might be familiar with a few of these things, but hopefully it will be new for some of you. Okay. So we want to start. One sec. So we're going to talk about part A, and the first part is going to be vector bundles via the notion of clutching data, or more generally the notion of transition data. Okay. And so what does it really mean? Well, so the point is we start off with a vector bundle of rank, let's say n, right? So this is rank n means usually it's a rank over our field, which is R or C. For these two talks, we'll mostly focus on K equal to C, the complex field. So, so we can choose local trivializations, which means B can be covered by open sets UIs, and there are maps PIs going from P inverse of UI to UI cross K to the N, whatever your K is. And these are again, so these are compatible with the usual map. So you have the projection map P from here to UI, and you have the projection on the first coordinate, which is compatible with that. And once you restrict to a pre-image, it's a linear isomorphism, because P inverse of a point is a topological vector space, and Kn has its own topology, so it's a linear isomorphism. So now once you have this, what you could do is you could define these maps Gij, and what are they? Well, they are simply maps from UI intersection Uj whenever they're non-empty to GLN of K. So how do you really get this? So what you really do is, let me use a different color. You start with an X, and so the way I index things, Gij is supposed to be the transition data when you go from the coordinates coming from Uj to the coordinates coming from Uy. Okay, so you sort of read from right to left. So it goes from J to I. So the point is you start with any X cross Kn, and you think of this as living in, of course, so let's say this, let's put it this way. Your X obviously belongs to Uj, but it also belongs to Uy, as you see. So the x has to be from here, but I'm thinking this is belonging to Uj. And so now what you could do is you could use Pj inverse to land into P inverse of x, right? Well, that's what the Pj inverse is. This is a homeomorphism. So if I didn't write it, there's a homeomorphism, and restricted to fibers, it's a linear isomorphism, and it's compatible with the projection map on both sides. So now from here, you can apply Pi, and this is going to land you in, again, by the trivialization into x cross Kn. And since both these maps are linear isomorphism, the composed map is a linear isomorphism, and it varies smoothly or continuously with x, as the case may be. So this is a map, a continuous map from the intersection to GL and K. And so these GIJs are called transition data because essentially you can build a bundle back from the transition data by literally starting with block bundles and attaching block bundles across intersections using GIJ. Okay? So the crucial thing to note here is that this GIJ satisfies the co-cycle condition. So what that means is it satisfies something like Ki equals identity, and this is the identity matrix or identity n cross n matrix on Ui intersection Uj intersection Uk. So you should think of this as a composition of 3 matrices for every point in the triple intersection. So yeah, so this, and in particular, it follows from the construction that GII is identity. This is called the co-cycle data. So any collection of such GIJs over UIs satisfying this can help you build a bundle back. So this is one way of introducing bundles. So let me write that as an observation in case people I don't know what color to use. Maybe this one. So observation 1. So you just have to play around a little bit. That transition data will produce a bundle. And you can recast the notion of isomorphism of bundles in terms of transition data, but it's a little more delicate because a bundle will give you lots of trivializations, right? So there's no unique choice of trivialization. So you have to be careful with the kind of equivalence relation you want to define on the GIJs along with the open cover. But it's an approach that one takes if you study vector bundles from a topological perspective. Okay? Let me mention a few properties of this transition data approach to vector bundles. You might have seen in one of the 3 talks before me on topological K theory that quite often this approach will specialize to an approach where we call this GIJ to be a clutching data, where you think of UI as a disk, Uj as another disk, and these 2 disks build a sphere. And in the intersection, you have a sphere of 1 lower dimension. Or more generally, this will be a cone on a space X. This will be another cone, and the union is the suspension, and the intersection is the space X itself. And the GIJ is simply going to be what happens when you glue 2 bundles over the cone along the X. So that would be the clutching data perspective that those who have attended the previous talks would have known. Let me mention a few properties. So we'll be using some of these, at least one for sure, and maybe more. Yeah, feel free to stop and ask me questions if anything is not clear. I intend for this talk to be more understandable than the next one, which will involve some computations. So the first one is if you want to ask what is the transition data for a direct sum or tensor product, right? So it turns out that if you give me an E, effectively giving me an E means you're giving me a trivialization and these collection of GIJs satisfying this. So if you give me 2 bundles, I could choose a common trivialization just by passing to a common refinement of both. So I'm assuming that both E and E prime have the same trivialization, but this will come with its own GIJ, right? So that's my notation. And if I have an E prime, this, even over the same trivialization, will come with its own. And again, here, technically, this IJ will run through M cross M, and this IJ will run through N cross N, because I'm not assuming they're bundles of the same rank. So technically, I should use KL, but I hope it's not too. Maybe I'll just for once I'll write it. This is KL. Okay. So now the claim is, and this is something you can try and have fun with. This, if you look at this, so this is obtained from the clutching data, which is you look at Gij 0, 0, and Gij prime. So you form this. So each Gij is a matrix. So you look at, so given an X, sorry, I think this is Ij. I'm sorry about that. Confused. It's Ij because the indexing is the same. Okay, because they're indexed over the same common trivialization. So it's still the same. It's the same Ij, just that this is an M cross M matrix and this is an N cross N matrix. So I can stack them diagonally and produce an N plus M cross N plus M matrix. And this will again satisfy the same cocycle data, right? So this, when you produce a bundle out of that, what you get is a bundle isomorphic to E direct sum E prime. Okay, so that's one thing. If you ask what about E tensor E prime, well, your guess would be as good as mine. It's the natural guess anybody would make. Well, how do you get this? Well, given two matrices, you can always talk about its tensor product. Like whatever definition of tensor product of linear operators, if you do this, then this is going to give you another cocycle data, and that's going to produce a bundle for you, which is E tensor E prime. Okay, so this. All right. Any questions so far? Okay. So 3, which takes a little bit of work, and this is probably the best source of this that I know of, is Steenrod's book, Topology of Fiber Bundles. But it's sort of, and so if you want your bundle to be isomorphic to the trivial bundle, how do you detect it in terms of the GIJs? Obviously, if all the GIJs are identity, then the bundle is trivial, but usually that's not going to be the case. So it says that E, your bundle, is isomorphic to epsilon n k. So this is my notation that I'll use for the trivial bundle of rank n over whatever the base field is, right? So I think in one of the previous, in Mohit's talk, he had used n lower bar, but they all stand for the same thing. So n lower bar, epsilon n, they stand for the trivial vector bundle of rank n over the appropriate space. So this, happens if there exists maps hi from ui to gln k. So you're looking for maps from the trivializations to gln k, such that what happens? This is kind of crucial, such that your gij that you have, so this is a matrix valued map, and this is defined on ui intersection uj. You want that to be the product of these matrices. Okay. So this inverse makes sense. I'm not saying that Hj is a homeomorphism. I'm saying literally evaluate Hj at a point that's an invertible matrix, take its inverse. That's what Hj inverse means. And then you left multiply that with Hi of the same point. So whenever you can find such His, that Gij equals this, you can show that the bundle is actually trivialized. In fact, you can show that two bundles are isomorphic if there's a variant of this which works. So you'll have Gij, Hi, Gij prime, Hj in a certain order, but that's what this notation means. Okay. Okay. And maybe one more property before we go on to actual bundles over S2. So, okay, so let's see. Yeah, so this is something most likely was proven, that any vector bundle over disks or contractible spaces are trivializable, right? So let me just recall it. So any vector bundle over disks, contractible spaces, because all you need is a homotopy of the space to itself, homotopy connecting the identity map of the space to itself to the constant map. to any reasonable point, okay, or contractible spaces. The vector bundle is trivializing, right? Okay. So so for instance, if you wanted to ask what about a bundle over Sn, well, you can think of a trivialization of such a bundle by looking at the sphere minus the north pole and the sphere minus the south pole. They are homomorphic to disks, and then the bundle is trivializable over each of the hemispheres, but they intersect over an open band around the equator. Okay, and so topologically, you can just deform the open band to the equator itself. So the entire clutching data or the entire transition data boils down to a map from a thickening of the equator to GL and K. But remember that the equator, so if your bundle, if your sphere is of dimension M, then the thickening of the equator is really a thickening of Sm minus 1, which is the equatorial sphere. So looking for a map from Sm minus 1 to GL and K. That's all this Gij is. Okay. So in particular, and this was, I think, used in the last term. So any E over Sm, right, is the E of rank n, let's say, okay, where Sm is classified by a map of the form F, which goes from the equatorial sphere to GLN K. Okay. So I'd like to just make one remark here. So this is what you get. So you can show that if you have such an F, you can build a bundle and vice versa. Any bundle gives you a clutching data and everything works if you put isomorphisms on one end and homotopic classes of maps. But here you can assume that this map actually is homotopic to a base map, meaning a point goes to the identity and so on. So in fact, this homotopic class of maps in the appropriate setting will simply become based maps from M-1 sphere to GL and K. And for those of you who have seen higher homotopic groups, that's literally the definition of M-1th homotopic group of this space, okay, like GL and C or GL and R. And the point is, if K is C, then GL and C is, of course, a large group, but you must have seen in a course in Lie theory that GL and C deforms to the unitary group, UNC. And since deformation retract preserves homotopic groups, you're as good as, to compute M-1th homotopic group of GL and C, you're better off computing the M-1th homotopic group of UN. And that is essentially where Bott periodicity comes in, that it, or at least not Bott periodicity yet, but if you want to classify complex bundles of rank n over the M sphere up to isomorphism, that set is exactly equal to the M-1th homotopic group of UN. Okay. So in particular, if you take S2, your M is 2. So if your M is 2, what happens? If your M is 2, you see that, so for let's say, I don't know, rank, yeah, so rank NEN over S2. This is all such bundles up to isomorphism. This is in one-to-one correspondence with phi1 of, well, GL and C, but as I said, GL and C deformation retracts to UN, so it's phi1 of UN. And one knows that this is actually Z. Okay? In fact, this is Z even for U, which is the direct limit of the US. So yeah, so in particular, if you take n equal to 1, you're saying there are countably infinitely many complex line bundles over S2. And we'll explicitly say what those are in a moment. But that's sort of my recollection for the vector bundles part. Okay? Now we'll go on to explicit bundles over S2 and deduce a relation. Are there any questions before I move on to that?
Sir,
yes.
Is this also true for real vector bundles?
You mean which one?
This bijection.
Yes, so if you so the point is, if you take any vector bundle, it will boil down to, as I said, if you take a real vector bundle, then the clutching data will say that it's classified by maps from Sm-1 to GL and R. In the case of GL and R, the issue is GL and R is not path connected, right? It has two components, GLN plus and the matrices of negative determinant. So you cannot say GLN. So what you could say is GLN R deformation retracts to ONR, but ONR has two components. So whenever you're saying I'm looking at the homotopic groups, I mean, usually you would have to choose which component to go in. So if you're doing oriented vector bundles, you will have an analogous statement which will say that up to isomorphism oriented vector bundle, real vector bundles over S2.
Okay, yeah.
In correspondence with pi 1 of SON.
Okay.
Because GLN plus R deforms to SON. If you want the other one, then you have to do the other one. So yeah, so that's the only issue. But that GLNC is path connected, GLNR is not.
Okay.
So yeah, so if your SM-1 is path connected, it has to land into one of the components. If your M is 1, that's like a trivial case. You're talking about bundles over S1 that you can, deal separately anyway, right?
Yeah. Thank you.
Okay. Any other questions? Okay, so let me. All right, great. So now we're going to talk about what did we do here? Okay, this is. Now I'm going to talk about. Over S2. Okay, so I mean, S2 sort of means different things to different people, and probably it's good that it's that way. So S2 for a topologist would be the unit sphere in R3. For a complex analyst, it's the one-point compactification of C, the Riemann sphere C hat. For an algebraic geometer, perhaps it's the projective space P1 or CP1. So the point is, this is a manifold. It's a smooth manifold, but it's also a complex manifold of dimension 1. So let's start off with the bundles that you already know, right? So what are the bundles that we know? The first bundle that you obviously know is the bundle TS2, the tangent bundle. And this is a real rank 2 bundle. It's actually an oriented bundle because S2 is an oriented manifold. Fine. But as all of you know from the Hairy-Ball theorem or otherwise, that there is no nowhere vanishing vector field, which means there is no nowhere vanishing section. They're equivalent to saying that there's no nowhere vanishing vector field. Okay, so we have this bundle. We also have this other bundle called gamma. I'll denote all the projection maps by P, fortunately or unfortunately. So here you sort of think of this as CP1, right? So what is CP1? CP1, recall, is basically the space of lines. So this is L. L is a 1D complex subspace of C2, right? This is a projective space built out of lines passing through the origin in C2, and you can give it a topology coming from that, or topology any vector bundle over simply connected basis over. Yes, that's true. That's true. But I mean, all I'm saying is that in this case, you can use that too if you want. Sure. So in fact, for S2, we'll see that something stronger is true. Okay? So it will turn out that any complex vector bundle will actually be holomorphic. I mean, that's not true in general. Okay, so you have this CP1. It turns out that's as a complex manifold equivalent to S2, where S2 being the standard unit sphere in R3. And so what is the bundle over it? So this is called the tautological bundle. So this by definition is going to be all things of the form L comma V, where L of course is a line and V belongs to L, right? So this, remember, is by definition a subset of CP1 cross C2. Because all you're saying is you already have this bundle, CP1 cross C2 lying over CP1, just a trivial bundle of complex rank 2, and then you're saying look at this sub bundle L comma V, where you're only choosing vectors in C2 which lie in the line L itself. So this has a name. This is called the tautological. So gamma is called the tautological bundle, and this is not. It's not anything specific to S2. This will work over any CPN. You can do the same thing. CPN has the same definition. You will have one-dimensional complex subspaces of C to the n plus 1. So this will be CPN cross C to the n plus 1. The same definition. Okay. So tautological line bundle. And once you have the tautological line bundle, you can construct many more line bundles out of it. Namely, you could look at gamma, you could look at gamma tensor. So let me, you could look at gamma tensor gamma, you could look at gamma tensor gamma, tensor gamma, all the way dot dot dot. Here again, the tensors are happening over C because the bundles are complex bundles. Okay, so these are all one-dimensional complex line bundles, or they are of complex rank 1. So you have all of these, but you also at some point realize that you also have gamma star, which is the dual, right? So I didn't talk about the dual in terms of the clutching data, but you can do it the same way. So there's the dual, which is, so what is the definition? This is going to be the dual in the usual sense, the linear algebraic dual. But now you have to, so whenever I write epsilon 1, it means the complex trivial line bundle. I'm looking at, you know, like fiber-wise, all C linear maps. So that is itself a bundle of complex rank 1. And this will have its own powers, right? So now you can look at gamma star, tensor gamma star, and all the way. Okay? And in between, you have, of course, epsilon 1 C. Okay? So if you note that, you know, this should really play the role of 0, and I'll explain what it means in a second. This should play the role of 1, so to speak. This is like 2, this is like 3. This one is like -1. It's like the inverse of gamma in a certain sense. This is -2, and all the way. Okay. Ignore these numbers if it's confusing. For those who know what it is, you know what it is. It will be related to the Euler class and so on. But you do have these complex bundles, and you see that you already can see, at least without any proof. But if you take it on faith that these are integer worth of complex line bundles. And we have seen that there are exactly an integer worth of complex line bundles over S2. So maybe this is the full list once you know that they're all non-isomorphic. Okay. Okay. So so we'll use a notation. Since I'm calling this the tautological bundle, let me add this thing over here, because there's always this confusion. I had this confusion for a long time. So usually topologists are happy with this being the tautological line bundle and the dual being what it is. Algebraic geometers tend to sort of prefer this to be the natural generator, and they call this the canonical. In this context, the canonical line bundle. So the dual of it. And so all these things have a notation. So whenever you take powers of this, so this is also often denoted by, this is also a notation denoted by O of 1. Okay. It's just a notation. So which means if you go by this notation, this thing is going to correspond to O of -2. This is going to correspond to O of -3. If the notation doesn't make sense to those who haven't seen, ignore this. Okay, so this is O of 0, whatever it is, and this thing is obviously O of 1. This is obviously O of 2, and so on. Okay. All right. So yeah. So let me just yeah. So one sort of thing that we'll note, I think I just be consistent with what I did. Yeah. So one of the things one observes through one way or another is that any complex line bundle over, yeah, everything in this section is over S2, is So any complex line bundle over S2 is okay for some things. So that's the full list. Okay. And there are many ways to show this. You could, if you know a bit of classifying spaces, you could say that the main line bundle, classifying everything is the half bundle, which is the bundle gamma, and then everything is just tensor powers of it, and or its inverse. And it turns out gamma star is the inverse of gamma as far as complex line bundles are concerned. Okay, so fine. So at this point, you could say, what about rank 2 bundles and so on and so forth. So in a little later, I'll make a remark regarding a theorem which I'll due to Burkhoff and perhaps later on due to Grothendieck, which I'll only mention in passing, but it's a nice theorem on its own and somewhat tangentially relevant, which characterizes all bundles over CP1 or S2, they're the same thing. And then that is somewhat more powerful than what we need. Okay. So, but right now we are saying any complex line bundle looks like some tensor power of gamma. So whenever I say gamma tensor minus 3, it's to be interpreted as taking gamma star and then taking 3 tensors of gamma star. Okay, because there's no gamma inverse. Gamma inverse is gamma star. Okay, so if you go to rank 2 bundles, well, there are many rank 2 bundles. Yeah, so one maybe homework or for those who are interested in the audience. So you have all these bundles, right? And it turns out this is also a complex line bundle. So the question is, which one is it? It has to be one of, like one in the list, right? And so you can try to figure out using Euler characteristic or Euler class. It will turn out that TS2 is actually going to be isomorphic to gamma star gamma. Okay? So you could use explicit transition data to show that if you want. But okay. So yeah. So let's try to do the clutching data perspective. So which means you are looking at we change this to color. So we're looking at, let's say, D minus, and this by definition is C. We want L. Okay, fine. So we'll use the CP1 model. So this is on all lines in CP1 such that L is spanned by, so L is the complex span, obviously, span of the vector Z, comma 1. Yes, that's true. Yes. See, as I said, there are many ways to, if you assume that the classifying space theory has been built, that's one way to do it. I'll state a few results along the way, which is somewhat more refined than using the classifying space machinery, because it'll give you a distinction between complex bundles treated as holomorphic bundles, and there is a distinction there. So I mean, you have to. So discussion is topological, but I'm just making remarks along the way which might connect with other things which are not necessarily topological in nature. So yeah, this is just a response to comment by Origin, I think. Anyway. Yeah, so we look at all the lines which are spanned by elements of the form Z, 1, where mod Z is less than or equal to 1, and D plus, as you can imagine, is going to be same thing. L belongs to CP1. In that L is the span, but now it's going to be 1, Z. Okay, and for mod Z. All right, and so you can convince yourself that these two literally are homomorphic to 2 disks, closed 2 disks. Their union is all of CP1, because any line is either spanned by some vector. You can always normalize and assume that the right coordinate is 1 or the left coordinate is 1, because it cannot be spanned by 0, 0. And the intersection will actually end up being a circle. So in this case, if it's the same thing, it will be a circle. So so if you want the trivial, so what do we want to trivialize? We want to trivialize. Yeah, so we were looking for the transition. So what we're looking for is the transition data for gamma. So let me mention that, otherwise I'll myself lose track of things. Transition data. So this is what we're trying to write down once and for all. Okay. Okay. So, well, you first write down the trivialization. So what is the trivialization? P minus is a map from P inverse. So P is my map from gamma to this. So here, recall that P is my map from gamma to CP1. Bundle map. So P inverse of D minus to D minus cross C. And what should this map do? So this map really, let me write it down. So I'll use this. You choose a line spanned by Z1, and then you're choosing some vector in that line. So that vector is of this form, right? And where do you send it to? Well, we send it to that line, obviously. The line has to go to that line, and we send it to lambda. Just project onto the second term. Okay. Similarly, you will, let me, oh, sorry. What happened? Spending choose, this one. Yeah, I'll just try to save some time. So then you have a P plus, this is P plus, this is P plus. So here we have to change things a little bit. Right here, and that's it. Yeah, okay. I think we're more or less done. So 1z, and then this is of the form lambda 1 comma z, and this is 1 comma z, and then lambda, right? So this is the the trivialization. Okay. And so what is the transition data? So you can convince yourself that the so what should be the transition data? So you realize that the transition data, if I write it as G plus minus, that means it goes from the D minus to the D plus, the bundle over D minus to the D plus. But it is technically over the intersection, which is the S1, and it lands in GL1C, right? Because the bundles are complex line bundles. But you see that S1 is already, so what is GL1C? This is nothing but C star, right? And S1 is a subgroup of C star. And in fact, it turns out that this is the inclusion. So this is just a matter of checking that the transition data from D minus to D plus is literally the inclusion of S1 in the group GL1C. Okay? Which essentially means you take two bundles which are trivialized over the disk, and as you flew along the equator, you identify one copy of C with another by a rotation by Z as your Z varies over the equator. That's what produces the tautological bundle or the Hopf bundle. It's also called the Hopf bundle, for those of you who know what it is. But for others, just treat it as what is defined. Okay. So now we know what the transition dates for the other ones are. So are there any questions so far? Okay. So what would be the transition data, let's say over the same plus minus for gamma tensor 2 direct sum epsilon 1. So again, epsilon 1 here is a complex line bundle. So I'm taking a line bundle gamma tensor gamma, adding a trivial line bundle with a complex rank 2 line bundle. By one of the properties I said, the transition data for this just multiplies. So it's going to be, for every Z, it's going to act like Z on the copy of C. This is Z acting on a copy of C by multiplying by Z. That's what this action means, right? So this should really be Z squared, 0, 0, and 1, right? The 1 coming from the transition data of this, the direct sum tells me I have to form the matrix by putting the block matrix form here. This is Z squared because Z goes to Z is the transition data for gamma. So gamma tensor 2 has transition data Z into Z. This is G plus minus of Z as Z varies over the equation. Now, what about G plus minus, let's say, of gamma, direct sum gamma? Well, this is even easier. This was Z, this is 0, this is 0, this is Z. So that's what it is, right? All right. Fine. We have two bundles which have the same transition data. Well, sorry, I think I spoke too soon. They don't have the same transition data. My claim is that these two transition data are homotopic because you have one map from S1 to GL2C and another map from S1 to GL2C. I'm claiming that these two maps are homotopic, and hence the bundles formed out of these two, which you already know, are actually going to be isomorphic. Okay, that's the claim that I'm going to make, and I'll write down a short proof of that. Are there any questions so far? Okay. Let me move on to the next page. Okay, fine. Yeah, sorry for the slight delay. So my aim is to now show that these two maps. So what is the aim? The aim is to now show that G plus minus for O minus 2 direct sum epsilon 1 and G plus minus, sorry, this is a minus for gamma direct sum gamma are homotopic. And there are many ways to do this. So I would just give you a quick way to do this. So the point here is, again, one of the things that was, I think, asked earlier, GL2C is path connected. You wouldn't be able to do this in GL2R, although things are not real valued anyway. The fact that GL2C is path connected tells me is path connected. So this tells me that I can find a path, okay, in GL2C joining the matrix, let's say the identity matrix to the matrix 0, 1, 1, 0. And we'll see why in a moment. Okay? I'm claiming there is always a path like this in GL2C. This wouldn't have been possible in GL2R because this is determinant -1, this is determinant +1. The intermediate value theorem would tell you that you have to land in singular matrices at some point. In over C, this is possible. So you just construct such a path, and then you simply write down this H, which is, so H is now going to be a map from S1 cross 0, 1. And this is what this map is. It's simply going to be, you put Z 0, 0, 1, you put omega t, which is this path. Right? So this is your omega of t. So it starts at 0, ends there. And then you put 1, 0, 0, Z. And then you put omega of t. Then it will turn out that this is the desired homotopic. If you want an explicit, so at 0, t equal to 0, you're going to get, as you can check, Z 0, 0, Z. And at t equal to 1, you'll get Z square 0, 0, 1. So if you are interested in explicit such omega t, what would such an omega t look like? Well, you cannot really do the rotation because the usual rotation will land you in 0, 1, -1, 0, but then you have to connect -1 to 1, avoiding. And so there are plenty of explicit maps. I'll just give you one because there might be students in the audience who might want to work out things. If not, just, take it for what it is. So this is cosine t. You have sine pi over 2t. And you could put cosine, let me drop this a little bit more. Okay, sorry. Is this readable, what I'm writing?
Yeah, it is.
Yeah, so sine pi by 2t, and this kind of ends here. So you really want to sort of just do the usual rotation matrix, right? The point is that wouldn't work because that would land you in -1 here. So what you do is you basically now want to gradually go from -1 to 1 along with the rotation matrix, but that means you have to put in a factor of minus e to the I pi t. And then you put the usual sine pi by. So this is one choice. There might be several choices. It doesn't matter. I mean, you can always show that there is a gamma, omega. You don't even need the formula. I'm saying there's an explicit one. Anyway, so this tells you that So this leads us to our, I guess, third observation, which is going to be very crucial, which is gamma tensor gamma direct sum epsilon 1. And again, from now on, whenever I say epsilon 1, epsilon 2, they are all complex line bundles. So it's not to be confused with epsilon 1 R. Okay? This is gamma direct sum. Okay? And we'll soon see that this is going to be a crucial relation that we will exploit. Okay. So yeah, so one remark. So I have two remarks. One is sort of elementary, the other one is more serious. The elementary remark is this statement is also true if you do it in the real setting, which means gamma is your Mobius bundle and your base sphere is S1. So over S1, which is RP1, you also have the Mobius bundle, which is also denoted by gamma, fortunately or unfortunately. And I'm claiming that the same statement would be true if you take the Mobius bundle, direct sum the Mobius bundle. That's a real rank 2 bundle over S1. You replace this with epsilon 1 R, so that's a trivial real bundle, and you direct sum that with Mobius tensor Mobius. And this isomorphism will still be true as real rank 2 bundles over S1. But it's much easier to show. I don't know if people have any comments, you can say why you think it might be easier to show in the case of Mobius bundle over S1. So one reason why it's easier is that one knows that the Mobius bundle, tensor the Mobius bundle, is actually a trivial line bundle over the circle. So the left-hand side actually becomes trivial. And it also turns out that the Mobius bundle, direct sum the Mobius bundle, is trivial because you can produce two linearly independent sections. Okay. So I won't have time to talk about sections of bundles and how it leads to projective modules, and that's kind of the connection with algebraic K theory. You'll see more of it in other talks. But that's the idea, that you show that Mobius bundle direct sum itself has two linearly independent sections. In fact, you can even visualize why it's trivializable. You just have to build a model and so on. So that's much easier. Okay? But my main remark is something that I want to point out because it's quite often, not taught or learned anywhere in some sense. It's a beautiful statement. So the remark is the following. Let me use a different, maybe blue again. So yeah, so the remark is that so it's basically, I think, goes back to Prof. This is probably 1909, and also Grothendieck, who kind of gave the modern proof, but the original proof was kind of algebraic and essentially due to Bott. 1957. So they basically showed that. So it turns out that any complex bundle over CP1 is holomorphic. So holomorphic means that the transition data appropriately are like biholomorphisms and so on. So yeah, so not all complex bundles by definition are going to be holomorphic, but it turns out every complex bundle over CP1 is holomorphic. For CP2 and CP3, it's still true. Although I'm not an expert on this, but I think these are much recent results and it's certainly hard to prove. So assuming that, they are now saying, look at any complex bundle over CP1, which is S2. It is a holomorphic bundle. But now you're asking about a classification of holomorphic bundles over CP1. So so if you have two complex bundles as holomorphic bundles, they'll not be isomorphic. Okay, but as complex bundles, they will be. Okay. So that's the thing. So they're saying that any holomorphic, the statement is any holomorphic. If you don't know what holomorphic bundles are, just this is the problem. Any holomorphic bundle, just take this as a statement which is interesting on its own, and you can read it up later. Or CP1 is of the form. This here. Yeah, it's of the form of rank, of rank holomorphic bundle over CP1. Make this again. Complex RAM n obviously is of the form O B1 direction BM, where these are non-decreasing integers. So D1 is less or equal to D2. Okay. Yeah. So that's the setup. And what are these OD1? So these are gamma star tensor D1. If D1 is positive and if D1 is negative, this is gamma your tensor minus D1, the usual. So this is so a consequence of this or otherwise, you can try to show. So I mean, this is the classification of holomorphic bundles over CP1. Okay, so you should note that when I look at this, right, versus epsilon 2, so this is the trivial complex bundle of rank 2. They're isomorphic as complex bundles, but they're not isomorphic as holomorphic bundles. So they're iso as complex bundles, not iso as holomorphic bundles. Okay? So there's something to be sort of said about this. Okay. Anyway, so as I said, this already gives us a handle of what a bundle over S2 looks like, even up to this refinement of holomorphic bundles. But we'll not use the full power of this thing. Okay. So any questions so far? That means 4 by 8. Yeah, fine. So now I want to sort of recall briefly, some of it will be known, so I'll be quick here. The K groups, the reduced K groups, and sort of what would be the K tilde and the K for S2 with the things that you have seen so far. Okay? So let me put it as A, B. This is basic, let's say, properties. No, Arijit, so I am not sure whether that's true. See, the point of anything, see, even this question of a vector bundle over a contractible space being trivial is very refined and hard if you go outside the topological category. So in the algebraic setting, this would lead to Sayre's conjecture and Quillen-Suslin theorem. So if you say that you have a vector bundle over the affine space, is it true that the vector bundle is trivial? So the point is the attaching maps and the trivializing functions are all morphisms in the appropriate setting. They're not necessarily continuous maps, right? So you might need biholomorphisms and so on. So it might be true, but I'm not sure of an immediate reference. I mean, this lifting, this bundle lifting thing that you saw in Mohit's talk, that is entirely a topological construction. That it's hard to imagine that will work in generality over the algebraic setting or the complex analytic setting. So, yeah, so we want to sort of talk about this a little bit and apply this to S2, and then at the end connect with one version of Bott periodicity. Okay, so I mean sometimes people work in this setting, and this is just a minor aesthetic thing for us. It's not. I'm not going to get too much into categories. So for those who are used to categories, top star is the category of all based topological spaces and maps between them of the appropriate kind. That means objects are a topological space equipped with a base point. So it's written as x comma x0. And then you also have this category top, which is the usual category of topological spaces and continuous maps. Okay. So quite often when we talk about reduced K theory, we are often working with base spaces, and you could always always give a map from here to here. If you have a base space, ignore the base point, you get a space. How do you get a base space from a space? Well, you attach a disjoint base point and call it the base point of the new space. It's like X disjoint union star, and star is the new base point. So there's always a map this way as well. Okay. Anyway, so so the point is you start with a base space. So this means I already have this inclusion, right? And so sometimes I'll just drop the curly bracket. It's understood that this is the set consisting of x0. There should be no confusion otherwise, okay? So this induces a map I upper star, and where does it go? It sort of goes from kx to k of x0. But remember, this is just a, this is just integers, because any bundle over x0 practically is just, I mean, a literal bundle is classified by its rank, and then if you take the group completion of the positive integers or the non-negative integers, you just get z, right? So this is z, and this. So now you can talk about it's a map of rings, and you can talk about its kernel. And so you could say, well, I define k tilde of x. So x is secretly a base space, so it comes equipped with x0. So you might say this is the definition of k tilde for base spaces. So this is going to be the kernel of I star, right? So one way to think of this would be, you can think of this as, I guess, the in the difference notation, class of E minus class of F, but E and F have the same rank. So it's just formal difference of two vector bundles over X having the same rank. Okay? Or you could think of it as a formal difference of E and the trivial bundle of the rank of E. And we have seen this earlier in one of the previous talks, that E minus F is the same thing as E plus G minus F plus G, and you can choose G so that F plus G is trivial, at least if X is compact, Hausdorff, and all of that. So you could think of this as elements here being generated by class of E minus the trivial bundle of rank E. Okay? It turns out there's a different definition of k tilde, which is equivalent, that you can talk of bundles up to stable equivalence. Sometimes that's useful, but let's start with this other definition. And you always have a map from X to X0. So this requires a choice of a point, but you always have a map that way, right? So you also have this collapse map from X to X0, and this will induce a map C upper star from K of X0 to K of X. And in fact, it's not hard to show that this will induce sort of a splitting, right? So K of X basically is isomorphic to Z. Okay. Okay. So because when you include X0 into X and project it, that's identity. So that basically says that, see, if you go from here and back to I star, that's the identity on Z to Z. So that sort of gives you splitting. Okay. So, all right. So I want to connect this definition of k tilde dot k for S2 with this observation that we had, which is this. Where did it go? This one, the observation 3, right? So what is this saying? This is saying gamma tensor gamma plus the trivial bundle is isomorphic to two copies of gamma added, but this addition is literally the addition in vector bundles or in K theory, right? So let's use that. So you should think of this as 2 gamma. So 2 gamma means gamma plus gamma. 3 gamma means gamma plus gamma plus gamma. And this is, okay, whatever it is, gamma tensor 2, and this is adding like the trivial bundle, okay? So let me, yeah, so I what I want to say here really is that what I want to say is this. I want to say that this should be interpreted as gamma 2. Gamma 2 means gamma tensor 2, so that's a bad notation, unfortunately, but we make it a bit more precise. Direct sum, I think the notation that was used earlier was 1 for epsilon. Let me use epsilon. So this is what we're saying, right? So forget that. I'm saying they're literally isomorphic. So obviously, as classes, they'll be the same. Okay. So in other words, this is equal to this, and this is 2 gamma, right? This is just notation, but you don't need to add or subtract anything. This is literally equal up to isomorphism classes, so their classes are the same in K theory. I'm saying something similar would be true if you apply induction, and if you keep tensoring this with gamma and use this rule, you can simplify this, and you can get something in here. Okay? So let me move on to the next page. So yeah, Dipankar, just one request. Is it okay if I take like 10 minutes more?
Oh yeah, actually the lectures are 1 hour and 30 minutes. So
Yeah, no,
we
no, I know.
started 15 minutes
I
late.
know it's 4:30, but since there was this
No,
technical.
we started for 15 minutes late.
Okay, sure. Okay, so yeah,
Go
so
ahead.
my observation here is again, so this is observation, and this is pretty easy to show from the original thing and then applying induction or whatever, is that if you look at gamma tensor n plus n minus 1 epsilon is epsilon 1, right? So this is the same thing as n. Or if you want to imagine this in K theory, you would say this minus this is 0, right? So this is going to be true. It's not going to be true like directly. There's going to be some epsilons, some copies of trivial bundles that you have to add here and there. But in the K theoretic setting, this would be true. Okay? So you could use the earlier observation, the main relation. Yeah, so by the way, the relation that we had here, I could write it. So this relation is quite often phrased in this form. So it's quite often phrased. So you bring everything to one side, and then this is like x squared. This is like +1. This is -2. So it sort of looks like h minus 1 square is equal to 0, right? Where you think of h as gamma or the class of gamma, the multiplication is tensor, the addition and the subtraction is the usual plus, and the subtraction is the inverse in the K theory, and then 1 is the trivial bundle. So this should remind you of this. Somehow it's saying that in K theory of S2, when you look at the class of gamma as an element, and you look at this element in K tilde. Now this is a genuine element in K tilde because my H is gamma and my 1 is epsilon. So the formal difference of gamma and epsilon is an element in K tilde of S2 because they're both bundles of rank 1. This is saying that in the ring structure, the square of itself is 0 because essentially of this. Okay. So this is going to be a useful thing. So this is not true directly as bundles, but it's true in the K theory setting. Okay? So you could prove this now in many ways. You could prove this directly by induction, or if you want to use Grothendieck's result, you know literally what any bundle looks like. So in any case, and I think this is something we had seen again in Mohit's talk, but we sort of deduce, from this or otherwise. I mean, not that you need this particular thing. I just wanted to, put it out there. So you deduce that K tilde of S2 is actually Z, and this is generated by gamma minus 1C. So quite often in most, I think, modern literature following Athia, perhaps you'd be, if you look it up, you'd be calling this H for the hyperplane bundle, and this to be 1. And so the element that you'd be denoting this by would be H minus 1. Okay. Anyway, so yeah, so it's generated by this, and it's generated additively, obviously. So if you look at yeah, so one more, maybe I should add one more relation. Okay. Sorry. it went up. So okay. So yeah, there's one more observation 4. Let's put it this way. Observation 4 A and B is that if you look at class of gamma to the n minus class of epsilon, excuse me. So this is going to be n into gamma minus. This is also something you can show. Okay? So the point is, anyway, so this is generated additively by this thing, and there's a relation. The relation is generated by this with trivial multiplication, and the trivial multiplication I've already seen, because literally gamma minus epsilon tensor gamma minus epsilon is 0. Okay, great. So now let me define the reduced, the general reduced k tilde minus n's and k to the minus n, and then make a comment regarding some version of Kuhn's formula. So most of you might have seen some version of Kuhn's formula either in Dirac homology or in singular homology or in other kind of context, that you have two spaces, you take their products, and then this k tilde or h lower star or h upper star or phi I are invariants, and you want to talk about the invariance assigned to the product versus the appropriate product of the invariants, which would be a tensor product or a direct sum, as the case may be. Right. So let me give you a definition, and then we'll go on to the So so these might have been defined. I just wanted to state it for coherence and completeness. Okay, so you want to define k tilde minus n of x to be, by definition, this is the usual k tilde that you have seen for Sm x if x belongs to top star. Recall that top star means this is the based, the category of based topological spaces. And so I guess suspension was perhaps defined. Let me give you a quick. Was suspension discussed earlier? Probably, right?
Yeah.
Okay. So here, of course, there is one slight point that I would like to make. Since this is a base space, you're talking about the reduced suspension and not the usual suspension. So when you read, usually you have this and then you have this, right? So this is just for any space, because what you do, you basically look at x cross 0, 1. So look at the cylinder, and then you essentially, like collapse all of this to a point, collapse all of this to a point. What you get would be a picture which you commonly see, and you say that this is your suspension. Or you say, I take a cone, and then I glue them along. So this has no requirement of a base point. Whereas here, this is usually for, the right suspension in the category of base spaces. And you do the same thing. You have a cylinder, which is x cross 0, 1. Okay, but now the point is x has a base point. So that base point traces an interval. So now what you want to do is you want to collapse this, but you also want to collapse this spine along it. And that's going to be, so, there's a quotient. So this, if you collapse this x0 cross interval, will give you this, but this is technically a different space. So when you have a base space, this is the reduced suspension applied n times. If you apply once, twice, and so on. Okay, so we raise this. Yeah, so I'm assuming people are aware of these constructions. So now I want to define the usual ones for the usual k, and you do the same thing, k minus n of x. How do you define this? Well, x is not going to be a base space, it's just in top. And well, you create a base space out of x. What you do, you take x disjoint union star, and then, so that's called x plus, right? So what you do is maybe I should here. What I'll do is x. Sorry, yeah. So x plus this x is Artesian with the usual, topology of x belongs to top. So this is by definition the reduced of Sn. Okay. So that's our definition. So we'll talk a little more in the next talk regarding why it is defined as k to the minus n. So the negative k groups are not the positive groups and so on. Ideally, I mean, there are enough reasons, but ideally there is no pointed suspension to use the notation sigma x. No, all my SNs that I'm using here are reduced suspensions. So this depends on what you. Okay. Yeah. So yeah. So the point is that there's no inverse of the suspension functor. You can suspend a space. You cannot really desuspend the space. Like you can loop a space, you cannot really de-loop a space. So you can, but then you have to go into the language of spectra and so on. But in any case, so this is what the definitions are. So the thing that I would like you to note is the following, that whatever these definitions are, if you look at the product space, x cross y, there are obvious projection maps, right? So I keep this way, there are obvious projection maps, one to x and another to y, right? So this is, let's say, PR2, PR1. You might say these are base spaces. There are natural inclusions, but there will be natural inclusions if these were in the base setting, right? So let me erase this and write it this. So we do have these maps, right? And now similarly, we have this, but then we also have, let me use red. We also have maps like this, I1, let's say, and I2. So this thing is happening in top. This thing is happening in top star. So what is this map? Little y goes to x0 comma little y. I have the base point in both spaces, so I know where to send. Similarly, little x will go to little x comma y0. If I have a base point for x and y, then x cross y is also a base space with the base point x0 comma y0. So in the base setting, I have maps both ways. In this thing, I don't have an obvious inclusion. There are many inclusions, but the point of this is that you could define a map mu. So let me use a different, because we're going to talk about this map mu. Point is that there's a map mu, and where does it go? Well, it goes from kx tensor. So this is a tensor over z. I might stop writing that, but it is understood, right? So I'm saying there's a map like this. Well, the map is sort of induced directly at the level of bundles. So you already know that if you have a bundle over x and a bundle over y, you can produce a bundle over x cross y. And how do you do that? So this is induced by, I have a bundle E over x, I have a bundle E prime over y. So given this, I can produce a bundle over x cross y. What do I do? I basically look at PR1 star. I pull back the bundle E. That gives me a bundle over x cross y. And then I tensor that with the pullback of E prime. Pullback of E prime is now a bundle over x cross y again. And that's going to produce and the map is induced by this. And so if you want to phrase Bott periodicity in a certain form, you'd want to say that you're asking a very pointed question. When is this? It's a map of rings. When is this an isomorphism of rings for some special spaces Y? So in particular, you're interested in putting Y equal to S2, and you still have a map from Kx cross Ks2 to Kx cross S2. And you're asking when is that, whether it's an isomorphism. And so the Bott periodicity in that version says that yes, that is an isomorphism. There are different versions of Bott periodicity depending on which proof you choose or which version of which description of K groups you start with. But it's a specific instance of a Punnett formula kind of thing if you want to phrase it very loosely with Y equal to S2. Okay, so this is. There's one more remark that I want to make before I at least state two versions of Bott periodicity and then maybe show that one implies the other and prove the main version, leave the proof for the main version next time. Okay, so let me finish up this section with one more remark, which I wanted to make. And I'll not talk too much about it today. Maybe next time if it's needed. I don't think we'll need this that much. So yeah, so the remark is, sorry, what did I use? So if, sorry. So if xy belongs to top star, so they're base topological spaces. So then it turns out, see, if you think about this, where did it go? So this mu, see, kx is z. So if x and y were base spaces, kx formally is z plus k tilde, ky is z plus k tilde. Sorry, k tilde y. So when I tensor, I'll get z tensor z, that's a copy of z. Z tensor k tilde y over z, that's a copy of k tilde y. K tilde x tensor z over z, that's a copy of k tilde y, and then the rest is k tilde x tensor k tilde y, right? Here I'm going to get z tensor k tilde x cross y. But you have to keep in mind that inside x cross y, there's a subspace called x wedge y, which is you join x and y along x0 comma y0. And so somehow you want us to talk about relative k groups and so on to actually prove this. The proof is not hard, but you have to develop those definitions. So whenever you're looking at this map, the z will go to the z. And if you look at the reduced k groups of x and the reduced, the reduced k tilde of x and the reduced k tilde of y, that will ideally map to k tilde, but not of x cross y, but for x smash y. And from a homotopic theoretic point, this is kind of expected because the right sort of notion of producing new spaces is not really the product, but really the smash product in the context of base spaces. Okay. In any case, so then we have map mu. I'll call it mu tilde because it's induced by mu. So this is a map from k tilde x tensor k tilde y to k tilde x smash y. So what is x smash y? So recall that if you haven't seen this, x smash y is nothing but you look at x cross y, and inside you have x cross y0 union x0 cross y, right? So you have a distinguished copy of x and a distinguished copy of y. They both agree exactly at x0, y0. You take that and you just quotient the entire x cross y by this. You get a new space. So if you know what this is, fine. If you don't, then have fun playing around with what happens when you smash two spheres. You take an m sphere and an n sphere. You can show that the smash product will actually be an m plus n sphere. Try it for S1 smash S1. I think it's a fun exercise. Okay. So it turns out there's a map like this, and in fact, it follows that if mu is and isomorphism. We don't know in general whether it's true, then so is mu tilde. Okay. So this is just a like a side segue kind of, I don't know. Okay, so this is just a remark. I mean, there's an induced map and this is an isomorphism, then that's an isomorphism. So if you expected an isomorphism from kx tensor ks2 to kx cross s2, you would expect an isomorphism from k tilde x tensor k tilde s2 to k tilde x smash s2. Okay? But recall that k tilde s2, as we've shown, is just z and you're tensoring over z. So this part is simply gone. So you'd expect an isomorphism mu tilde from k tilde x to k tilde x smash s2, and we'll soon see what smashing with a sphere is. It will essentially give you the suspension back. Okay, so that's the last bit that I'll try to maybe convey and sort of. Okay, so any questions so far?
I had a question.
Yes.
In algebraic K-theory setup, we have a kind of Lodes product in K-theory, where we just have a map from Ki of a ring tensor Kj of that ring to K of I plus J of that ring. I mean, there is a map, and that's induced from the smash product of the classifying spaces of those GLR plus BGLR plus. So is there any kind of analogous thing in
Yeah, there will be. See, this is just the usual k tilde, right? So
yes.
when you find the full sort of like the k tilde which we have, you know, okay, so k tilde, so you might say, what about k tilde minus nx tensor k tilde minus my to k tilde minus n minus m of x smash y? Well, the point is that is by definition smashing with x. Sm, you smash x with Sm and you smash Sn with y, and then the induced map is obtained by smashing all of those, right? But then you can smash the two spheres together, that's Sm plus n, and then you can smash it with x smash y. I mean, all of these are appropriately sort of associative commutative kind of things. So you would get a map if you put all the upper indices to be k tilde minus m, k tilde minus y, then it will go to k tilde minus m plus minus m minus n of x smash y. You would get a map once you've defined the higher k tildes, or I mean the negative k tildes.
Okay.
Yeah. So yeah, I'll maybe, you know, like mention that next time if we get to it. So this is just the usual k tilde, but you're right. I mean, essentially it's the fact that if you take two spaces, smash them, and then smash with a sphere, it's the same thing as taking the individual spaces first, smashing with two spheres, whose smash is the original sphere, and then smash them, kind of. Yeah. Okay. So, right. So this is now getting into part B. B for Bott, but B for second, the main part. So this is Bott. Bott periodicity. So the first thing that you note is, in fact, there is a ring homomorphism from Z. I think most people would denote it by I'll call it T. It's simple. And I'm saying there's a ring homomorphism which is induced by the following. So what you do is, if you give me A0 plus, and all of you will immediately realize, or even can figure out before I finish writing, what this map is. So given a polynomial of degree n where the coefficients are integers, what do you want to do? So A0 is an integer, so you want to assign to it up to a sign which comes, you know, before the bundle, because an element in K3 is allowed to be E1 plus E2 minus F1 and so on. So this should really be the trivial bundle of rank EI. So I'm going to write it this way. This is a summation. This is sign of AJ, epsilon to the mod AJ. So this is the trivial bundle of rank absolute AJ, and then you tensor that with gamma to the J, right? And this again means, if I'm being pedantic, this means this is technically this, right? And then you sum over j is equal to 0 to n. Okay? So this is, if all the things are positive, this is a direct sum of bundles. If some of the signs are negative, it's an alternating sum appropriately. So this will define a map. It's a map of rings. And so what name do I give it? I haven't given it a name, okay? But anyway, the point that you note is that under this map, t minus 1 square goes to 0, right? This is precisely the relation that we proved. So which means this map of rings factors through and gives me a map. And now I'll denote that map with something. This, I'll call it lambda. So this gives me a map zt mod the ideal generated by t minus 1 square. There's a map from the ring map from this to this. Okay. And I'm claiming that this ring map is an isomorphism. So there are two ways to show this. You have already seen in I guess in Mohit's talk that this is z plus z. One way to show that is k of s2 is k of a point plus k tilde of s2, and both are z. And this is also as an abelian group z plus z. And in fact, you know that this is a surjective map because this map itself was surjective. So if you have a surjection from z cross z to itself, then it's you can easily show that that has to be an isomorphism. It has to be an injection, or you could directly show that this is a ring isomorphism. Okay. Yeah, if you want, you can even use the classification of bundles, using, I don't know, Bott or whatever. You don't need all of that. So the point is, this is an isomorphism of rings. Okay? So now let me state Bott periodicity version 1. So this is not Bott periodicity, but this is saying that if you're literally tensoring, so if you go back to the thing we stated here, this one, if you want to put ks2 over z, then you're tensoring with, instead of ks2, you can put z of t modded out by t minus 1 whole square. Okay. And so, as I said, it's commonplace to use capital H here instead of t if you are more inclined towards geometry, because H is supposed to stand for the hyperplane bundle. But to each his or her own. So let me state Bott periodicity. Okay, so this basically says that, and we sort of know what to say. The map mu from kx, and this again, recall it's a tensor over z. This goes to k of x cross s2 is an isomorphic. Some fortunate that okay, and so yes. Okay, great. And similarly, as okay, so this is version 2, and that's going to be in terms of the reduced thing. So the map mu tilde, and I'll put tildes here and I'll put tildes here. But as you have realized, this is z, and tensoring over z doesn't really do anything. That's going to change. Okay, and this is going to become like this. And this is going to change. Remember, this is k tilde of smash. Now recall what happens when you smash any space with S1. And we'll do it twice. So if you do it once, it's x cross S1, but so that's like a cylinder worth of x's, but then you have to collapse one entire copy of S1 and one entire copy. So if you do this, what you get is really, the reduced suspension. If you do it once more, you get the reduced suspension twice. So that's S2x. So this is going to go to k tilde. This is k tilde x because it's tensoring z over z. This is going to go to k tilde of the smash, but that's S2 of x. Okay. So I'm going to rewrite this statement. I'm just explaining why the statement that I'll write down should make sense. This will go into k tilde of the double suspension of x. And this is an isomorphic. Okay, great. So this is my okay, right. So yeah, so I'm claiming that version 1 implies version 2 because the point is there's an obvious isomorphism between k tilde x and k tilde x tensor k tilde S2. You simply take a class and multiply it with gamma minus 1, and then if mu is an isomorphism, mu tilde is an isomorphism. So that basically proves that version 1 implies version 2. Okay? So let me finish by saying why would this be useful, and you will see more instances of this in summing talk later on when you think of these k tildes or k's as exotic cohomology theories. The point is that this is telling you that if you suspend the space twice, take its k tilde, that's isomorphic to the original thing. So you couldn't really desuspend the space, but now you can. You can say that if there was some notion of desuspension, if I do it twice, using this twofold periodicity, I could define the positive k groups. So the upshot is going to be you're now going to actually define k tilde of, let's say, 2k of x to be just the usual k tilde, because you know that it's periodic on the negative side. And you define k tilde of 2k plus 1 of x to be k tilde of sx. So this is for k 0. I mean, you couldn't really have done this if you did not have a notion of periodicity. And these are going to define some kind of a cohomology theory for spaces, at least for compact Hausdorff spaces, let's say, or for spaces where every vector bundle has another vector bundle whose direct sum is trivial. We're using that all the time. Yeah, but we'll try to go through the proof given in Atiya's book and at least in part sketch a proof of this thing. There are many other proofs, and if there is time at the end, I would like to mention that this particular thing that we computed k tilde of S2, and if you apply this to x to be a point, you're saying k tilde of a point and k tilde of S2 is an isomorphism. They're both z. It might seem like a triviality, but the point that I would like to keep you to keep in mind is that k tilde of S2 is, you think of S2 as the projectivization of C2, right? I mean, that's literally what it is. But you think of the projectivization of C2 as C2 being the trivial rank 2 bundle over a point. So over a point, every bundle is just a bundle itself. But you can now try to generalize that. If you have any bundle over a space, you could try to projectivize that and ask what is the k tilde of its projectivized space as a k tilde x module, and so this is going to be enhanced to that setting as well. And you don't have to take x cross S2. So this x cross S2 is the projectivization of x cross C2. If you projectivize the trivial rank 2 bundle, you get x cross S2. But you could take any other rank 2 bundle over x, projectivize, you will not get x cross S2, but you get a non-trivial S2 bundle over x, and you can ask whether there are similar results. And we'll also talk about that a bit if there's time. Okay? So yeah, I'd like to stop here. So thank you.
All right. Are there any questions? Well, if not, let's thank the speaker. So we'll have another lecture next week. And I'm not sure about the other lectures in this in topological case. They might be cancelled. But nonetheless, we'll meet next week.
So
Thanks a lot for this lecture.
Yeah, I can send you these slides.
Yeah, please do.
Once I fix some typos, and if it helps.
Yeah, it will be uploaded in the website actually.
Thanks. Okay. Bye.